Hello everyone, I'm J Wildberger. In today's video, we're going to be looking at regions in the complex plane. So we want to exploit some of the arithmetic with complex numbers to be able to describe regions in the plane, sometimes called the Argand plane when we are discussing the complex number situation. Okay, so the complex plane, sometimes also called the Argand plane. So it's really the same as the usual plane, two-dimensional plane, but now with a kind of complex focus. So x and y axis are really the real and imaginary axis. So this is like the real axis. This is like the imaginary axis. And what we want to do is we want to describe certain kinds of regions. And the regions that we're going to be considering are things like, maybe, let's say we have a line like this and we want to describe all of those points. Or maybe we have a point here and we have a circle centered at that point. We might be interested in describing that region there. Or maybe we have a point like this and we're interested in describing this wedge-like region here, where the directions that we're allowed to go from this vertex are in a certain range, in a certain angular range. Okay, so those are basic kinds of regions that we can describe very easily with complex numbers, and we'll also be talking about combining them with the and the or operations, essentially unions and intersections. And there'll also be a slight subtlety, because sometimes we use strict inequalities and sometimes non-strict inequalities, and there's a little bit of a difference. Okay, so we're going to be using set notation. Okay, that's sort of standard in this course. I probably should just warn you that I'm not a big fan of set notation when it comes to describing infinite sets. I think finite sets are fine. So, for example, the set of n in natural numbers n, such that, say, n is between 3 and 1,000. Okay, that's a perfectly reasonable object because it's a finite set that you could actually put on your computer. However, if you, say, consider the set of x in the real numbers, such that x is between 3 and 1,000, well, this is quite a different kettle of fish for two reasons. First of all, the real numbers themselves typically are involving infinite decimals, which require an infinite amount of computer space. And then secondly, there's an infinite number of these real numbers in this kind of interval, so there's no way a hard drive could store this. Okay, so my preference is to think about this rather not as a set but as a type. Okay, and I'm not going to elaborate on that, but computer scientists think about describing objects in terms of types, not necessarily in terms of memory locations where things are stored. And I think that's another way of interpreting what we're doing today. So I will be using the set theory notation, but my own preference is to officially interpret those things in terms more of a type in the way computer science might. But anyway, it's not really going to affect the pictures that we draw. Okay, so let's start with the basic sort of geometrical connections between the complex plane and our two-dimensional space. Okay, so we have a complex number z right there. I'll always draw 1 and I just to orient ourselves. So I remind you, say if z is a plus bi, then the mod of z is equal to r, and that's going to be the square root of a squared plus b squared. Sometimes the square root of z times z bar is a little bit interesting, and I like to call that the quadrants of z. Okay, so that's the modulus of z, and of course that represents geometrically the distance between the origin and z. Okay, so this is actually a distance or a length. Distance between the origin O and the point z. Okay, the other kind of ingredient for polar coordinates is this angle here. So theta is, say, the arg of z, and that's the angle the angle made by the positive x-axis and the vector from O to Z. Okay, so let's just relativize those two notions. So now let's consider we have 2 points, maybe Z here and W here. Okay, so then we could consider the length of Z minus W. What's that geometrically? Well, that's just the length of this vector that joins them. That's the length of the vector. Maybe we could say vector from W to Z, although we haven't used that notation very much. But another way of saying it is the distance between Z and W. So, for example, if, say, W is maybe, in this case, something like 2 plus I, and Z is maybe something like 3 plus 4I, then modulus of Z minus W is the same as the modulus of, we just take the difference. Z minus W will be 1 plus 3I, and that's going to be square root of 1 squared plus 3 squared, which is the square root of 10. So that's telling us that this distance here, d, let us say, is the square root of 10. Okay, the other thing that we might gather from this relative position of W and Z is the angle here. So if we look at theta, which is the argument of Z minus W, what is that going to be geometrically? I might show it here. So here is a line parallel to the x-axis, and then here is the vector. This is the vector from Z, from W to Z, and then the angle theta right there, well, that's going to be the argument of Z minus W. So actually Z minus W as a vector would be the same vector down here, just translated so that it's starting at the origin. So that would be the point Z minus W, and then the theta is exactly the same as it is here. So these are the two angles are the same. Okay, so this is, we can describe this as being the angle made by a positive x-axis and the vector from W to Z. And I also remind you that capital arg Z minus W, so that's the principal value, sometimes PV, principal value of arg Z, that is by definition always in the range minus pi arg Z minus W less than or equal to pi. Okay, so that's good. All right, so now let's have a look at some examples of regions. First, some simple regions that we can describe using complex number language. So our first example will be the set of Z in C such that, let's say, the real part of Z is bigger than or equal to 2. Okay, the real part is bigger than or equal to 2. So here's 1. Here's I. Here's 2. There's 3. Okay, so the real part is really like the x-coordinate. So we're talking about all those points whose x-coordinate is bigger than or equal to 2. And that's going to be like a half plane, we could say. It's going to look like this. Okay. And note that the boundary that I've drawn, this vertical line here, this is the line where the real part of Z actually equals 2. And it is included in this region because here we have greater than or equal to. As another example, if we had, say, the set of z in C such that the imaginary part of z is less than 3/2, what would that look like? I'll draw it on the same picture. So here's I, here's 2I, somewhere in between would be 3/2 I. And then we're talking about those complex numbers whose y-coordinate is less than 3/2. So now we should put a dotted line here, actually through this point, dotted line, and then we're going to be talking about, say, draw it in this direction, this region. Yeah, maybe I'll use a different color. How's that? I'll use this color here. Okay, so it's going to be this region here. Okay, everything under the line, here's the line, imaginary part of z equals 3/2. Okay, and everything's underneath that. Good. Okay, so that's relatively simple. Let's do another kind of example. Suppose that we look at the z in C such that the argument of z is maybe, let's say, in absolute value less than or equal to pi/4. What would that mean? So we're talking about the condition that arg of z is actually between minus pi/4 and pi/4, with equality included because there's a less than or equal to here. So what does that actually look like? So here's 1, here's I. So we're looking at all those complex numbers whose argument is between minus pi/4 and pi/4. Pi/4 is 45 degrees. So one kind of boundary will be this one here, going down at minus 45 degrees or minus pi/4. And this one here going up at 45 degrees or positive pi/4. And the argument of z should be between these. So we're talking about everything in this region here. Okay. Good. Okay, now let's be a little bit more sophisticated and move these things around a little bit. So another example, suppose that we have the set of z in C such that z minus I in absolute value is less than or equal to 2. Okay, so now there's a modulus involved, the modulus of z minus I. So we have to recall that the modulus of z minus I is the distance between the point z and the point I. So we're talking about those points z whose distance to I is less than or equal to 2. Well, that's going to be a circle. Okay, so here is 1, here is I, 2, minus 1, 2I, etc. Then we are looking at all the points centered here, okay, centered here, which are less than or equal to a distance of 2 from there. That's a circle that's going to be centered here. So we have to draw a circle of like radius 2. So we could go like up to there. That'd be radius 2. And so this would be a circle, something like this. Okay. And we're talking about the points whose distance is less than or equal to 2. So it's the boundary of the circle together with its interior. Another variant on that, suppose that we had the set of z in C such that z minus 2 plus I is less than a half. Okay, so now it's a little bit trickier because we have to interpret this quantity here. We have to interpret it as a distance. So mod z minus 2 plus I, that's the same as the modulus of z minus 2 minus I. Okay, so then when we write it this way, it makes it clear that this is the distance. It's the distance between z and 2 minus I. So where is 2 minus I on our story? It is, here is minus I. So 2 minus I is right there, 2 minus I. And now we're talking about a circle which is of radius a half, okay, centered at this point 2 minus I. So here's about a half, okay. So it'll be a smaller circle like this, but the inequality here is a strict inequality. So we should actually replace this circle with a dotted circle. Okay, and look at the interior of that. So the actual boundary of the circle is not included. Good. Okay, so what about one with a bit more fancy argument? So let's look at an example. Let's consider the set of Z in C such that, well, the argument is between minus pi by 3 and between, say, pi by, I should make it a little bit more sophisticated. Let me do a little bit fancier. Let's say argument of Z minus 1 plus 2I. So that argument is between minus pi by 3 and, say, pi by 2. We have to be careful about the inequalities. Look at the inequalities carefully. That's a less than. This is a less than or equal to. So it's a little bit different there. Okay, and close brackets. There's a set. Okay, so we want to interpret this. So the starting point is to just rewrite this as a difference. So write z minus 1 plus 2I as z minus something. Okay, in this case, 1 minus 2I. All right, so that's a sort of starting point. That tells us that we're really talking about points in relation to the point 1 minus 2I. Okay, so let us draw things. I might draw it like this. So here's 1, here's I, and here's minus I, and here's minus 2I. And here is minus 1. Okay, so where is the point 1 minus 2I? Here it is, right here, 1 minus 2I. Okay, and now we're looking at those points so that the argument of z minus this point is in this range. So, for example, if z was over here, let's say, okay, then z minus 1 minus 2I will be this vector here, and we'd be talking about this argument that we're referring to is it would be this angle here. So what we're really asking is what z can we write down that will ensure that this angle here is in the range bigger than minus pi by 3 and less than or equal to pi by 2. Okay, so let's maybe I'll get rid of this one because you don't really need it, and let's draw the region. Okay, so minus pi by 3. From here, this is the angle of 0 in this direction. Minus pi by 3, that's like 60 degrees. Okay, so, but in the negative direction. And I'm going to dot it because there's a strict inequality there. Okay, and the other range is less than or equal to pi by 2. That means that angle there can go up to pi by 2 and including pi by 2. So it's going to be solid there. Okay, and so we're talking about all the z's which are in this range, in this big wedge, an unbounded wedge that keeps on going as you go up and to the right and down in these directions. Okay, that's the range of all points. And maybe we should just be clear, the argument is actually not really defined for 0. So argument of 0 is a problematic kind of thing. What's the angle of 0? It's hard to say. So it's better to leave that undefined. And so we should not include the point 1 minus 2i itself in this big set. Okay, so that's good. So now we could take these various things and put them together in various fashions. And I just need to explain that unions and intersections of regions are determined by, so unions are described by ors and intersections described by ands. So for example, suppose we had the set of z in C such that, say the real part of z is greater than equal to minus 1 and the argument of z is, say, between 0 and, let's say, 2 pi on 3. Okay, so let's have a look at what that means. Okay, so we draw our axes. There's two separate regions here, so let's draw them first. We'll label the axes. The real part of z bigger than or equal to minus 1. Here's minus 1. So this is a greater than or equal to, so we're including the boundary. There it is there. That's the first region. The second region, maybe I'll draw it in a different color. The point z, so that the argument of z is between 0 and 2 pi on 3. So there's the origin. Okay, it's actually not going to be included, so I'll make a circle. And points whose angle is 0 is in this direction, and angle of 2 pi on 3, well, that'll be between pi on 2 and pi, so it's like 120 degrees, so off in this direction, something like that. Okay, so this second region is this one here. And now we have to put them together with this and. Okay, so the and is telling us that we actually have an intersection. Okay, so what is the final result of that? Well, maybe I could do it on this region here. So the things which are in both of these regions will be what? So here, this is green. Here, everything that's both red and blue. There, and we should exclude the origin. That's a open circle there, and everything in here. All right. And with an or, well, then it's like that, but it's a union rather than an intersection. Let's do one example like that. So example, suppose we have a set of z in C such that z minus 3i, the absolute value is less than 1, or what else? Maybe arg of z plus 2 is equal to pi by 2. Okay, this is an or, so the or is like a union. The or is like a union. We're talking about points which satisfy either this first condition or the second condition. Okay, what does that look like? So the first condition, it's looking like a circle. It's a circle that's centered at the point 3i up here. There's 3i up there. And it's a circle of radius 1. So I'll draw it in blue. And it's less than, so it's an open circle. So we'll draw it like this. Okay, so we're talking about all those points. That's the first condition. And the second condition, argument of z plus 2 equals pi by 2. So where is what's z plus 2 referring to? So z plus 2, that's like z minus 2, okay? So we should be looking at the point minus 2, which is down here. That's actually a point on the complex plane. So we're looking at all those points z, so that the vector from minus 2 to z has an argument of exactly pi by 2. So what z are those? Well, those are the ones that look like this. So this kind of z here, that will work. But we should not include this point here. So in this case, the second set is just this ray that goes up in the vertical direction. And so what is the total set? Well, the set is the union of those things. So if I do it in green, it'll be this thing here, every point on here, not including the actual point minus 2, together with this open circle centered at 3i. Okay, so we have a flexible range of ways of describing relatively simple sets in the complex plane or the Argand plane. So I'll see you next time.